Hello everyone, my name is Qing from Dr. Jeremy Levy's group, University of Pittsburgh Quantum Institute. My topic today is correlations between magnetic and piezoelectric force microscopy at gated lanthanum aluminate strontium titanate interface. First, let me give a brief introduction to the system we have been using. Both lanthanum aluminate strontium titanate are insulators, but when we put these two materials together, a 2D electron gas will form at the interface. The conductance of the interface can be tuned not only by the thickness of LAO, but also the top gate and back gate electrodes. By applying voltage, the interface will undergo an insulator-metal transition. Many of the properties, such as spin-orbit interaction, electromechanical coupling, as well as magnetism, can be varied by changing the carrier density at the interface. Magnetism was first reported in 2007. This came as a big surprise, considering the bulk state neither LAO or STO show any sign of magnetism. A large negative magnetoresistance has been observed at the order of 30%. In 2011, Arundel studied the zero field code and field code magnetization as a function of temperature. The magnetization loop has been detected under different temperatures. Notably, a ferromagnetic response is observed as seen in the form of hysteresis loop extending up to room temperature. Torque magnetometry provides a way to directly measure the magnetic moment. These torque measurements reveals a large average amount, about 0.3 Bohr megaton per unit cell error. However, scanning squid microscopy provides a very small average amount, about 0.2 Bohr megaton per unit cell error. The origin of magnetism has also been studied. By X-ray magnetic circular dichroism and X-ray absorption spectroscopy, they found this in-plane magnetic order is related with titanium-3 character of the dxy orbit in an anisotropy T2G band. Electronically controlled ferromagnetism has also been studied at room temperature. Inspired by this newly reported phenomenon, we performed magnetic force microscopy on LAO-STO heterostructure. The heterostructure are fabricated by depositing 12-unit cell LAO on top of STO substrate. The heterostructure are patterned with circular top gate and concentric arc-shaped interface electrode. While doing the measurement, the tip and the top gate are both grounded, eliminating any electrostatic coupling. And the significant contrast of the frequency shift image only shows up when the positive voltage applied to the interface electrode. Under this condition, the sample is in an insulating state. And notably, this magnetic order only shows up when the tip is magnetized in plane. If the tip is magnetized out of plane, the contrast will vanish, which means that the magnetic order we observed has an in-plane direction. At the same time, the other aspect of the LAO-STO heterostructure, electromechanical response, has also been studied. First, the principal calculation has shown that the lattice distortion and the metal insulator transition has a connection. The lattice distortion are observed at the STO near the interface by using transmission electron microscopy. The lattice distortion is carrier density related due to Young-Taylor effect. When charge accumulated at the interface, titanium-4 will become titanium-3, and this will cause the elongation of octahedral and lead to the distortion of the interface. A specific piezo force microscopy has been performed to study the electronic nanostructure created at the LAO-STO interface. A side gate and a single nanowire are created by lithography techniques. While doing the PFM, both the tip and the side gate are grounded, eliminating any electric field applied across the LL and STO layer. And an AC voltage at the resonance frequency is applied to both ends of the nanowire. In this way, the electric field is only within the interface. The PFM, the piezo response, came only from the change of the carrier density. The effective piezo response string tensor element D33 has a linear relationship with the change of the carrier density, and the surface displacement can be calculated by integrate this string tensor with respect to the DC voltage applied to the interface. And there is a difference between both sides of the metal insulator transition point. When the sample is in an insulating region, the surface displacement is linear with the DC voltage, and when the sample is in an insulated state, the displacement is related with the charge accumulation. And this linear part is due to the LL polarization, so the interface distortion can be calculated by subtract the LL polarization part. Since top gate and interface electrode can effectively tune the carrier density at the interface, we performed this piezo force microscopy on top of our LU-STU heterostructure. A PFM amplitude channel shows a significant contrast when positive voltage is applied to the interface electrode. This is very similar to what we saw in MFM. While doing the MFM, the tip is kept at a constant height above the sample surface, and the tip is affected by the long-range magnetic force. So in this way, it provide a method to locally detect the magnetism. While doing the PFM, the sample is engaged with the tip is engaged with the sample surface, and it can locally detect the carrier density. Since we can do both PFM and MFM, it provides a way to study whether the magnetism is carrier density related. So we perform the PFM and MFM on the same sample error. First, we find the specific sample error and did MFM. We apply positive voltage to the interface electrode, and we saw as we decrease the voltage, the contrast becomes smaller. And then we change the tip to an unmagnetized tip and go back to exactly the same location. And we saw this similar change of the contrast when we're cycling the voltage. So here comes the question: why would the MFM and the PFM have the similar behavior? We studied the capacitance as a function of the DC voltage. We saw there is a huge enhancement of the capacitance near the metal insulator transition point. This is due to the charge accumulation. And we also performed the PFM on a fixed sample location under different DC voltage. The parametric plotting of PFM signal versus capacitance show the hysteresis loop is highly correlated. The small patches of magnetic domain we observed is due to the inhomogeneous distribution of the carrier density, and this inhomogeneous carrier distribution will lead to the different response of different piezo response. So both MFM and PFM are carrier density related. In this way, they are highly correlated. For short summary, MFM is used to search the magnetism at gated LU-STO system at room temperature, and the ferromagnetic phase will emerge when the sample is insulating and vanish when the sample is conducting. And PFM is applied to the same sample error, and the similar domain feature shows up when the tip is insulating. The origin of this correlation is carrier density related. Thanks.